Hi class, so this is a lecture on chapter 17.3. So we're well into our chapter on electrochemistry. In this chapter, we're going to be talking about potentials of those galvanic cells. So we'll be talking about electrical potential, and it relates to those cells that we talked about in the last unit. So I'm going to start my slide. And we have a PowerPoint worksheet to do as usual. And here's the PowerPoint slide. And so this is chapter 17.3 on electrode and cell potentials. And so we're going to describe or relate the definitions of what these potentials are. We're going to talk about those. It sounds sort of like potential energy, and that's what it is. And then we're going to interpret the cell electrode potentials in terms of the relative oxidant and reductant strengths. And those are the half reactions. When we looked at galvanic cells last time, we said we'd set up a galvanic cell by separating the half reactions into each side of the cell. Well, we're going to learn about the potential and potential energy in each of those in this unit. And then we're going to calculate cell potentials for cell reactions. And the worksheet that you see up there in the corner has some of the abbreviated notation we learned for writing galvanic cells. And from those, we're going to calculate the potentials that those various cells have. Okay, so let's continue. This is kind of a fuzzy slide, but what this shows is that we know that water spontaneously flows downhill and over a waterfall. And you can look at a waterfall and you know that the top of the fall has a higher potential energy to the bottom of the fall. So that's why the water flows down. You know, there's lower potential energy at the bottom. The same goes for these galvanic cells. So if you look at the anode and the cathode, if the anode potential is greater than the cathode potential, the electrons will flow from the anode to the cathode. So the electrons, you can think of the electrons as going downhill from a higher place to a lower place, if you will. Oops, no, okay. So let me go back. Oops, I'm going the wrong way. Okay, so in a circuit, the flow of electrons is the result of a electrical potential difference. And that occurs in our galvanic cell, that occurs from the redox reaction that's going on. But for that to happen, for the electrons to actually flow from one cell to another, the reaction has to be a spontaneous reaction. And though spontaneous reactions are reactions that allow electrons to flow from the anode to the cathode. And that always happens. So if the electrons always go from, you know, they're leaving the anode. That's what we learned. That's why the anodes where oxidation occurs. So they leave the anode and go to the cathode. Well, that only happens if the potential is right. Otherwise, it goes the other way. Okay, we learned that if a reaction is not spontaneous in one direction, it is spontaneous in the other direction. And so we're going to learn which electrical cells do operate spontaneously in the forward direction. That's what we're looking for. So in a galvanic cell, this potential is called the cell potential. And it's the property that is attributed to it is called a volt. We've all heard of volts. You may not think of volt as being cell potential, but that's what it is. So unit is volt. And what is a volt? Let's look at a volt. So it's a potential. And the volt, let me move my little thing here. It's in the way. There we go. So the volt is defined as joules over coulombs. Where joules, we know joule is an energy unit. So there are lots of units that we use for energy. Joules, calories commonly in chemistry, but there are lots of others. Ergs, we learned that a joule is a, kilogram per meter squared or something. I can't remember. I have to go back and look again, but there's lots of units that we can attribute to energy. Chemistry is joules and calories. And volts, so the volt is defined as joules per C. That capital C is not Celsius. It's not a temperature. It stands for coulombs. And coulomb is a charge unit of charge, current, excuse me. It's the coulombs of charge, which equals current. So the coulombs is related to the current, and the current is the flow of electrons. It's how many electrons. Our flow is a rate. It'd be like miles per hour. You know, if you were, how fast your car is going. Well, it's not exactly a rate. It's like how much. So it would be like how many cars are going down a highway, you know. So it's a flow. For water, it would be like cubic yards per second. So it is kind of a rate. It's an amount that's passing through a certain point, if you will. So anyway, the more electrons, the higher the current. And we measure that in coulombs. So what's happening now? Why isn't this? Oh, there we go. Okay. I don't know what happened to my slide. There it goes. Okay, so a volt is measured in joules per 1 coulomb of charge. So that the equation up there, V equals J over C, is 1 volt equals 1 joule per 1 coulomb. That's what that means. And 1 electron has 1.602 times 10 to the minus 19th coulombs. So it's not very much. But if you have a mole of electrons, if you multiply that six times, if you multiply this charge on 1 electron times 1 mole of electron, which is 6.02 times 10 to the 23rd, you get a lot of coulombs. And we're actually going to do that later on. We'll see that number is going to appear later on. In section 17.4, where we're actually use the flow of electrons to calculate the free energy that a galvanic cell produces. That's the next one, next chapter. So in a galvanic cell, the cell potential, which is in volts, is given here. So E cell equals the potential of the reduction reaction, half reaction, plus the potential of the oxidation reaction, where the reduction potential occurs at the cathode and the oxidation potential occurs at the anode. So in order for a cell to be spontaneous, or in order for a cell to generate voltage, the reaction has to be spontaneous. So E cell is positive for a spontaneous reaction, and it'll be negative for a non-spontaneous reaction. So that's what this fourth bullet point says. But it turns out that the potential for reduction and oxidation cannot be measured directly. Of course, you can't measure just a half of a reaction. You can only measure a whole reaction. So the way you measure is you get a cell and you have a voltmeter and you measure the volts. So there's no absolute zero for these. So the way that they're measured is it's a relative measurement. So the way what chemists or physicists have done is to set up a reference cell. So that a half cell was chosen to measure all others against. And the reference cell, I think that's in the next slide, is a hydrogen called a hydrogen. It's a hydrogen cell where the reaction shown here is the reduction of hydrogen, 2H plus 2E. 2 electrons goes to H2. That's a half reaction for the reduction of hydrogen ion. The reverse reaction would be an oxidation reaction. So this is called the standard hydrogen electrode, SHE for short. And at standard, so standard means standard conditions. So we're going to talk about cell potentials at standard conditions now for a while. And standard conditions are the same conditions we've talked about before for free energy and entropy and enthalpy. So standard conditions are 25 degrees C or 298 K, 1 atmosphere pressure, and 1 molar concentration. So that's what shows in this schematic of the standard hydrogen electrode. So you can see that the H2 gas going into this electrode is at 1 atmosphere, and the concentration of the acid H plus is 1 molar, and the temperature is 298 K. So this is called the standard hydrogen electrode, and the potentials for other half reactions have been determined against this. So how did we do that? Well, they assigned the definition, by definition, the potential of this is defined as 0. So the oxidation, the potential, cell potential for oxidation is 0, and the cell potential for reduction is 0. Now, I don't know if it's on here, but the potential for an oxidation reaction is minus the potential of the reduction reaction. We're going to see that later on. But remember I said if you, the reaction shown here for hydrogen is the reduction. But if we flipped it over and put the H2 on the left and the 2H plus on the right, it would be oxidation. Well, the E reduction is equal to minus the E oxidation and vice versa. Now remember, in addition to that, oxidation occurs at the anode. So we have E naught, the naught, remember, means standard conditions. E naught oxidation could be, the subscript could be E naught anode. That's the potential at the anode. E naught reduction would be E naught cathode. That's what we learned last time. So let's look at how these cell potentials are actually developed. So here's a cell that's set up, that's a reaction between the standard hydrogen electrode and copper. And if you run this cell, you'll realize that the spontaneous reaction occurs where the hydrogen gas, H2, is being oxidized. So it's the oxidation, the SHE is being oxidized, and the copper ion is being reduced. So we find the H2 going to 2H plus 2 electrons, oxidation, that is oxidation on the anode side, and copper 2 plus 2 electrons going to copper, which is reduction on the cathode side. So the because we're measuring this, remember our equation is the E cell is E reduction plus E oxidation. Well, E oxidation is what's occurring at the anode, and that is the standard hydrogen electrode cell potential. Well, what's that? That's defined as 0. So you plug in 0 there. You measure the potential, not the half cell potential, but the whole cell potential, and it's 0.337. So we have 0.337 equals the reduction potential plus 0. So the reduction potential, which is copper ion going to copper is 0.337. So there we have it. That's the standard half cell reduction potential, because it's reduction for copper. If we flip that over and we wanted to find out what the oxidation potential was for copper, copper going to copper 2+, it would be E naught oxidation. It would be the opposite, it'd be minus 0.337. You just put a negative sign in front of it. Now, once this is done, you can measure, once you know copper, you could measure, I think previously we saw copper and silver being reacted in a previous lecture. Well, we could figure out what the silver half reaction potential is. Once you know one of them, once you have a couple of reaction, you know one, and you have a way to measure the voltage with a voltmeter, you can calculate the other one. So here's another example of a redox reaction, this one between zinc and hydrogen ion, and we've done this in lab before. If you put zinc in a solution of hydrochloric acid, the zinc starts, or the solution starts bubbling, producing hydrogen gas, and the zinc starts dissolving to form zinc 2+ ions. So this is a spontaneous reaction. So being a spontaneous redox reaction, we know it's going to give a positive cell potential. And so let's split the half reaction. So the half reaction, did we split the half reaction? Haven't done it yet. So anyway, we have zinc going to zinc 2+, so that's oxidation. So the zinc reaction, the zinc half reaction is occurring at the, that's oxidation, that's going to be the anode, so that's over here. E oxidation is for zinc, and then E reduction is for the standard hydrogen electrode, SHE. Well, what's the cell potential for the SHE? It's 0. So we're going to plug 0 in there. And we come up with 0.762 volts, because we measured 0.762, equals 0 plus E naught oxidation, and that's for the zinc reaction. And so I've written this here. So 0.762 is the oxidation potential for zinc, going from zinc to zinc 2+ ion. The reduction potential would be the opposite. So the reduction, the E naught reduction for zinc going from 2+ to zinc is minus 0.762. All right, let's continue. So standard half cell potentials are commonly tabulated though for reduction half reactions. So when you measure the cell potential, let me go back. You said the cell potential is for reduction plus oxidation, but when you look at your table in the book, it's all for reduction half reactions. So that's called the table is called the table is called the standard reduction table for half reactions. There are also standard oxidation tables. In fact, when I was taking this course in college, we learned electrochemistry using standard oxidation tables. And somewhere along the way, teaching this subject, I don't know, somewhere along the way, the tables changed, and they've changed to reduction tables. Maybe that makes sense. You know, reduction occurs at the cathode. That's the ability to pull electrons away from another atom. That's what's happening. So the half reaction going on at the cathode is pulling the electrons away from the what's going on at the anode. And so when we look at these cell potentials for reductions, the higher the number, the higher the E0 reduction, the stronger that pull is for electrons. You could think of it as electronegativity. So it's kind of related to electronegativity, except electronegativity has to do with the attraction for bonding electrons. But one of the strongest species with the strongest reduction potential is fluoride ion, F-. not fluoride, fluorine itself, F. So fluorine, because it has a strong attraction for electrons. So F2 is a high reduction potential. Most of the elements with high reduction potentials are a lot of metal ions that they're positively charged, and they like to, some of the noble metal noble type metals like gold ion, Ag plus or Au plus has a strong reduction potential. So we'll see that. We're going to look at this table in a minute. We'll recognize which elements have high reduction potentials. So we'll talk about that a little more. In fact, here's the table right here. So here's a table of gold is at the top of this table. It has reduction potential of 1.498 gold 3 plus ion, not 1 plus. So 3 plus ion is on this table has the strongest reduction potential. So that means if you mix Au3 plus with anything else on this table, the Au3 plus is going to be reaction is going to occur at the cathode. Anything below it is going to occur at the anode. Remember, anode's oxidation, so it's the reverse reaction that occurs at the anode. So if you add Au3 plus, say Au3 plus nitrate, gold 3 nitrate, and you combine it with silver, well, you'd have to have the reaction would be silver, solid silver, which would have to be oxidized, would be at the anode, and the Au3 plus would be at the cathode. So remember, the reactions are opposite. The cathode's always reduction. So what happens at the cathode is as shown in this table. What happens at the anode is the opposite. And when you're comparing two half reactions, the reduction half reaction with the highest reduction potential is going to occur at the cathode. So I'll be repeating this over and over again as we go through. So here's another, just an extension, continuation of this table. This table is in your book or something like it. So let's look at another way. Let's look at these reduction potentials. I'm going to change this equation a little bit, and so that we can understand it in just terms of reduction potentials, not reduction and oxidation. So we know E reduction is occurring at the cathode, so we could put E not cathode. We know that E oxidation is what's occurring at the anode, and that's an oxidation reaction, but it's the opposite. If we put a negative charge, we know it's minus the reduction reaction that would be occurring at the anode. So we can describe the potential at the anode in terms of reduction, but we just have to change the sign. So when we do that, and here's a description, for oxidation of zinc is 0.76, reduction for zinc is minus 0.76. So in that last slide, we said that the last example, we had zinc and, I don't remember, zinc and, maybe zinc and the hydrogen ion electrode, that's right, zinc and SHE. And we said the oxidation potential is 0.76, but the reduction would be minus 0.76. So we can describe our cell potential then in terms of just reduction potential. So it's E not what's going on at the cathode. So it's reduction potential at the cathode minus the reduction potential for the reaction going on at the anode. So this is the E cell in terms of half of reduction, half reaction potentials. So how to use reduction half reaction potentials. The half reaction, this is what I mentioned previously, with a higher reduction potential. It's always the reduction half reaction that occurs at the cathode. And conversely, the half reaction with a lower reduction potential is always the oxidation half reaction that occurs at the anode. So you would flip the reaction with the lower reduction potential would occur at the anode, but it would be reverse. You have to write it as the oxidation half reaction. And what we said, we can end the way to calculate this by using the information directly off the tables without having to change signs. Is just say the E cell is E cathode minus E anode. So let's try this. So here's a reaction going on. So the reaction at the cathode, we're going to use E cell, E cathode minus E anode. The reaction at the anode, which is oxidation, is copper going to copper 2 plus. And at the anode is silver. It's being a reduction silver ion going to silver. And so I have the cathode, the reduction of silver shown here. So the cell potential off that table for the half reaction of silver ion going to silver is 0.7996. And the half reaction at the anode, so that anode, remember, this is the reduction for copper to 2. This is the reduction reaction, half reaction of the reaction going at the anode. Okay, that's plus 0.337. But what we know is that reduction isn't occurring at the anode, it's oxidation. So let's flip it. So we have copper going to copper 2 plus, and the potential then is minus 0.337. So these first two values we got off the reduction table, but we know the second reaction isn't a reduction, it's oxidation, so we flip it. But this is where we just add, now we're going to add the two. We're going to add the cathode reduction minus anode reduction, and this is where the minus comes in. Okay, so we have minus anode means minus 0.337. We add those together, and we get 0.463 volts for this cell. So let's uncover this voltmeter up here, and we get 0.46 volts for the cell. So that's how it works. So the next thing we're going to do is look at a worksheet and try it out. So I'm going to finish. I think that's the end of the slideshow. So I'll finish the slideshow and stop the screen share and go back to our worksheet here. So I started this worksheet already. So let me brighten it up a little bit. Let's see if we can brighten it up. There you go. Okay. So hopefully you can see that. So this is worksheet 29. And there's always an introduction on most of the worksheets. So this pretty much goes over, it summarizes what I just covered in the lecture. So let's get into it. So what I want to do is I'll do problem 1 and 2. So I'll do 1 and 2, and you guys do 2 and 3. And I think this worksheet is 1. I think I want you to turn it in. I don't quite remember, but anyway, I'll do 1 and 2, and you guys do 3 and 4. And 4 is an interesting one. 4 is kind of an open. Let me go down to that. 4. 4, there isn't one correct answer. So in 4, it says write the half cell reactions for an oxidation reduction that creates a cell with a potential greater than 2.6 volts. So what you have to do is look at that table and use a combination of reduction and oxidation that will give a cell potential greater than 2.6 volts. So that's all you need to do. And remember what's going on at the cathode is oxidation. Now a good cathode, a good reaction at the cathode might be that zinc. The zinc reduction potential was really, remember, it was minus 0.776. That's pretty. At the anode, that means the cathode would just have to be 2.6 minus 0.776, I think it was. 2.6 minus 0.776, if I'm correct, would be, you need a reduction potential of 1.8 or greater. So you might need something that has a little bit lower reduction potential than zinc. Because I don't think gold was that high. I don't quite remember what gold was. I don't think it was 1.8. So anyway, that's what you have to do. So you figure it out. Come up with a cell potential that's greater than 2.6. So let's do, let me do these. So number one is, so the way this is written, remember our notation, this is the anode on the left. So we have iron going iron 2 plus 2 electrons. We're going to figure the cell potentials for these. They might not be spontaneous. If they're not, if the E cell is not positive, then it's not spontaneous. And then the other cell potential is the reduction of silver on the right. So we have silver ion plus 1 electron going to silver. So this is the cathode, that's reduction. This is the anode. And we know our E cell is equal to E cathode. And you can look up at the top, it says that right up here. E cell is E cathode minus E anode. So I'm going to look this up on the table. So the iron reaction, Fe, let's see, we're looking for minus the E for the, so these are reduction potentials. So the reduction potential for the iron is, let me look, its reduction is minus 0.447, minus 0.447. So that's off the table. I'm looking at this table from our, from your book. And the reduction potential for silver, silver's up there, let me find silver. Silver is 0.7996. So silver is plus 0.7996. So what we want to do is we'll take the cathode minus the anode. So we have our E cell is equal to, you see that E cell is going to be equal to 0.7996 minus a minus 0.447. Remember, these are all in volts. So our E cell is going to be 0.79, let me see, 0.7996 plus 0.447 comes out to be 1.246, or if we use our sig figs, we can only go to 3 decimal places, so it's 1.247 volts. So that's it. So for the second one, let's see. So our second reaction is lithium going to lithium plus. So at the anode, we have lithium is being oxidized. And at the cathode, we have cobalt being reduced. And so since cobalt's being reduced, that means cobalt, supposedly, if it's a spontaneous reaction, is going to be above the lithium on the table. And I'm looking at this table in your book. And I can't seem to find cobalt 3 to cobalt 2. I find cobalt 2 to cobalt 0. but not cobalt 3 to cobalt 2. So I really need a better table. I do find lithium though. So the lithium is minus 3.04. So lithium, so our reaction is lithium going to lithium plus 1 electron. That's our half reaction. The reduction potential for lithium is minus 3.04. That's pretty big. I mean, it's weak. Lithium is not a good oxidizing agent. So these substances that have high reduction potentials are pulling electrons away from them, so they're strong oxidizing agents. So this table is showing the at the top of the table are the strongest oxidizing agents. At the bottom of the table are the weakest oxidizing agent. So lithium on this table out of the book is right at the bottom. So we have the lithium, and I need cobalt 3 plus 1 electron going to the reduction potential from cobalt 3 to cobalt 2. And I don't have that. It might be on the PowerPoint slide. It might be on the slide because I think the slide is a more complete list of reduction potentials in lecture. Let's see, cobalt 2, come on. Nope, it's not on that one either. So that would be, might have to look that one up on the internet. I guess I can't do that one because I can't find the reduction potential for cobalt 3 to cobalt 2. So I'll leave it like that. I think you guys can finish. I'll have to look it up on the internet. So you do finish number 2 for me, do number 3, and then number 4. Come up with a, everybody, there's no right answer for problem 4. The right answer is that you set up a galvanic cell that has a cell potential greater than 2.6. So that's it for this lecture. I'll sign off for now, and the next lecture will be 17.4, and we'll talk about the energetics, free energy, equilibrium constant, all those things we talked about previously in chapter 16. So take care, and I'll see you next time.